last section of this is entitled Linear State Estimators, and as I explained previously, the job of the estimator is to produce the state vector for use by the feedback controller. I'm going to introduce the topic in a rather broad way in a section called state reconstruction. So this outlines the problem which faces us, that of producing the state vector. And then I'm going to talk about how you produce a linear state estimator, how you design it, and how it produces the state vector for us. And this will lead us, hopefully, in a series of intuitive steps to a design of estimator known as a prediction estimator. It'll produce the state vector for us, but the method that it uses to do it uses a output measurement which is one sample out of date. Or seen another way, you're predicting the state one sample in advance of the most recent measurement you've got. And it gives you generally a good performance, but one which you can improve upon by using the most recent measurement to produce the state vector in the same sample period, and that is called a current estimator. Unfortunately, the name rather implies that you are estimating electrical current, which you're not. You're using the current output in the estimator algorithm. So that's one way in which the basic estimator design can be improved. The other way is in cases where some of the states also appear at the outputs of the system. So if we have a system, let's say, with 4 states in it, but one of those states is the output or appears at the output, then what is the point in estimating that state when you can measure it? Right? It's an internal variable, but it's also a measurable internal variable. And in that case, you can simplify somewhat the estimator equations by only estimating those states that you don't know. But the technique that you use to design the estimator then changes quite a lot. And the estimator which results is called a reduced order estimator because its order's gone down by the number of measurable states. And so I'm going to show you that way as well. The main advantage in the reduced order estimator case is not a performance improvement, but a computation efficiency. And then finally, I'm going to summarize all the steps involved in controller design and introduce you to something called the separation principle, which is, well, it's a justification for doing things this way. I guess that's what you would call it. The quotation in this section is one I took rather randomly from a book by David Leuenberger, who's perhaps the father of linear state estimation. You may have heard his name come up in connection with estimators, and sometimes the Leuenberger estimator is the name that's given to the sort of classical linear state estimator that I'm going to describe next. Now here's the fundamental facts that we've got to contend with. Providing you know what the state vector is, you've got complete control over all the closed loop eigenvalues. I've shown you that through the design of the K-matrix you can place them anywhere you like. So that's nice. But unfortunately, direct measurement of all these states is either impractical, uneconomical, or just downright impossible. So we have a problem on our hands. We have to obtain the state vector for use in the controller. And this is the job of an algorithm, which is variously called an estimator or an observer. They're exactly the same thing, it's just that different people give them different names. And because I feel that the term estimator is more descriptive of what it actually does, I'm going to call it an estimator. This is how it fits into the control loop. I've described the controller, which consists of the gain matrix K, the input matrix N, and possibly an integrator or a series of integrators. And that involved the input, the feedback state X, and it outputs the control effort U. But now the state vector is going to be produced for us. It's by an estimator. It's estimated. So this hat symbol here, I'm going to call this X hat because it's easy to say. We write it with a caret over the top, this sort of hatty, carroty thing. It indicates that the vector is an estimated vector rather than the real vector. Now, your estimator will produce not only the state vector estimate, but also an estimate of the outputs. And so you've now got an estimated Y as well as an actual Y. Now, because most of the time when you construct an estimator, you're going to do it in software using a computer, I'm going to continue this section completely in the discrete domain, because although the theory applies equally well to continuous time estimators, in practice, you're not going to be building one of those. It's going to be an algorithm, so you're going to be working with discrete time systems. So we're going to use phi gamma C and D instead of A, B, C, and D in the equations. And in practice, yeah, they're implemented using a computer. So what you've got is an estimator, which in principle is a model of the system. And if you've got perfect knowledge of these matrices, it behaves in exactly the same way as the real system does, and therefore y hat and y are going to be exactly the same number, and x hat is going to be the same as the real, but invisible x, which exists inside the system description. The problem is that you don't always know what phi, gamma, C, and D are, and you don't always know either, and this is just as big a problem, what the initial conditions are of the system. You don't know what the initial state is here because you just don't know it. So why should it be that this state vector should be correct? And so what is done in practice to make this state vector correct is, well, you use feedback. And the only thing that you can use is the output, because you know what the actual output and the estimated output are. So you hold this, you construct a feedback loop around the difference between them. Right? So you create a signal, a time function, which is the difference between y and y hat, and you enclose the estimator in a feedback loop, like this. You put that difference into the estimator, and you therefore force y and y hat to hopefully converge on the same answer. Now, it turns out that this will correct for any initial state error. So when you switch the thing on, you don't know what it is. This will eliminate over time the state error. It will force the estimated and actual state to converge on the same number. But it doesn't completely correct for plant model error. When you've got plant model error, you will still get a small mismatch in the estimated state. And there isn't much you can do about that, because if you've got not complete perfect knowledge of the plant, that those estimate errors can't possibly be right. I mean, how do you know that they are right? You've got to base your measurement, base your estimate on something, and that's the thing you hang your hat on and say, I know what the model matrices are, but if you're wrong, well, it's going to be a little bit of difference. Now, as I said before, this would be called a full state estimator because it produces for us all of the elements in the state vector. We can simplify the algorithm somewhat if some of the states also appear at y, and the way we do that is through a reduced order estimator. But if that's the case, there are times when it's still preferable to produce the full state vector, even though some of them are measured. And the reason is the noise that is present in measured variables. You've got sensor noise, electrical disturbance, all sorts of things that come in there. So even when you can, some people still choose to use a full state estimator, even though some of the states are measurable. State reconstruction problem then, just to ring fence what faces us, is to determine all the system states, that's the full state vector x of t, using y and u, because those are the two things that you can get hold of, y and u, and the knowledge of the state matrices, which you hope is correct. Now, of course, I mention this in passing because I have to mention it, but it's downright obvious, isn't it, that if C is square and invertible, and you know what D is, there are times when you can get hold of the state vector at the output. But it's never going to be the case. You're never going to get a square matrix with C, and if it is it going to be invertible? It's not, right? So let's discount the trivial case right now, because if that was the case, you wouldn't need an estimator in the first place. I'm assuming that that's not the case, and you'd be lucky if you ever come across a situation like that. Now, just as controllability guaranteed that we could find a controller that produced the eigenvalues we were looking for, for state feedback control, so the property of observability guarantees that we can produce the state vector simply by observing the output. Remember, observability is a property of coupling between the states and the output. It says that we can detect and determine what the states are doing just by measurements of the output. That's exactly what we're doing with an observer. So before we proceed to design anything, we should check that our system has the property of observability before we do anything. And then you've got any observable system of order n, you can construct an estimator of the same order. And here's the thing, you can place the poles of the estimator, because it's in a feedback loop, it's going to have its own poles, you can place them arbitrarily. And I've already told you about the difference between full state and reduced order estimators. Now, here's how you do it. This is the equation of a discrete time linear state estimator. It's a first order difference equation, x hat of k plus 1. So it's obviously a difference equation involving the estimated state, x hat, equals CE times x hat of k. CE is going to be the linear system estimator matrix, the system matrix for the estimator, plus L, some matrix called L, times y of k. So this is where the output, the measured output is coming into it, plus a fiddle factor over here, z of k. That's something that we're going to feel free to choose and use for our own evil purposes later on. Okay, z of k. So remember that, that's the linear state estimator equation. Now, we want the estimator error to converge on 0. Right? So, in principle, assuming that you know for the moment what the actual state is, if you subtract the estimated state from the actual state, you'd like that to be 0. So what we'll do is we'll look at the left-hand side of this and subtract x hat of k plus 1 from x of k plus 1. All right, so x of k plus 1 equals this. You know what that is. That is the system matrix. Phi times x of k plus gamma times u of k minus the first equation on this slide. So it's minus phi times x hat of k minus L times y of k minus C times k. Now we can simplify a little bit because we've got a couple of terms here involving x of k. So we've got phi minus LC times x of k, and then the other terms are unchanged. And now what we'd like to do is to have a nice simple equation that we can use to design L. And this doesn't look very much to me like a nice simple equation, but we can make it nice and simple by choosing this matrix CE to be that. Because if you do that, this CE equal to that means that we've now got these two matrices the same, and we can say x minus x hat here. That's the actual estimator error. So we've got the estimated derivative error, the state derivative error here, and the actual state error over here on the right. See that? We do that. So we make CE equal to that. And the only thing that makes it awkward is we've got a couple of terms hanging off the right-hand side. But that's no problem because we've got the fiddle factor that we can come to and make that equal to gamma times u of k, and all our problems go away. So that choice makes x of k minus plus 1 minus x hat of k plus 1 on the left, and then this matrix here, C minus LC times, well, it's the state error on the right, state estimator error. So there's the choice we make for CE and Z. And if I define the state error now as the difference between x and x hat, this looks a lot like a first-order difference equation, a homogeneous one, and it's something that we can use to design L. Now, if you take yourselves back to the in first part of the chapter 7, when we looked at state feedback control, we began by looking at the homogeneous system. There was no input, was there? There was just a feedback matrix. And what was the closed-loop state matrix? It was A minus BK or phi minus gamma times k. And it was just a first-order difference or differential equation, and that's exactly what we've got here. So there's no reason why we couldn't use Ackermann's formula or pole placement on this, and that's in fact exactly what we do. It's just that instead of phi minus gamma k, we've got phi minus L times C to work with, and the process is going to be exactly the same. Providing you choose the eigenvalues of this matrix to be inside the unit circle, it will guarantee that the error will converge on 0 as k becomes infinite. Now, I want to step you through this in 2 or 3 steps just to show you what it looks like diagrammatically. Here then is the original estimator equation that we started with, x hat of k plus 1 equals c times x of k plus y of k, L times y of k minus c of k. So, x hat of k plus 1 equals CE times x hat of k, so there's these n delay elements present, plus L times y of k, plus C of k. So all I've done here is show in diagrammatic form the linear state estimator equation. Now we made 2 choices. We made the choice CE equals L minus LC, C minus LC, and Z equals gamma times U. So first of all the Z, well that's easy because it's just gamma times U, so that's coming in on the right, on the left. And now CE equals C minus LC. So what I've done here is replace CE with C minus LC. Now here's the thing, we can redraw this, right, because this is phi minus LC. Watch what happens next. Right, no difference. This was phi minus LC. So we've got phi minus LC. Right? It's an equivalent block diagram, phi minus LC. This is the same as this. It's the linear state estimator, and doesn't it look similar to the ABCD model that we presented earlier? It's just a model of the plant, and the only difference is that we've got this feedback matrix coming in here, which, look, it's the difference between the measured and the estimated output. Clever, isn't it? See how it works? So this, then, is the matrix that determines the eigenvalues of the estimator. And you can put them anywhere you like. We're no longer constrained in our choice of the estimator eigenvalues by having to keep the control effort within limits or by worrying about saturation. It's numerical considerations, mainly, that constrain L. And therefore, you can make these estimator eigenvalues as fast as you like, almost, and you typically put them much further to the left, or, since it's a discrete time system, much closer to the origin of the complex plane than those of the controller. Because they will contribute to the dynamics of the system, but you don't want them to contribute much. You want the controller that you just designed to dominate the dynamics, and therefore the controller is doing the job of fixing the performance. All this is doing for you is producing the states. So you choose L such that the eigenvalues of phi minus LC are very fast indeed compared with those of the controller. Now, in the previous case, I did rather simplify things without drawing your attention to it, because when I substituted for y of k up here, I just took y equals c times x, and I didn't harp on the fact that it was a non-zero transmission matrix, but it was, and a lot of the times it will be, because it's a physical system, and usually the D matrix is zero. But if it's not, let me show you the effect of that. Now we substitute y of k with cx plus d times u. C times x of k plus d times u of k. And we go through exactly the same steps as we did before. We subtract the estimated from the actual state in an attempt to make a nice stable estimator error. And the only thing that's any different now is that we get gamma minus LD times u, right? Rather than just gamma u, there's an extra LD term that appears over here. But it's not a problem, because all we do is fiddle factor it out. You choose z of k now so that it equals gamma minus LD rather than just gamma times u. So there's the difference, and you're back to exactly the same set as you did before. So, in fact, the presence of a non-zero D matrix does not influence the estimated dynamics at all. The only thing that it does influence is your choice, z of k. And when we draw it all out, guess what it does? It makes our diagram look even more like the model of the actual system, because it is a model, right? There it is. It's the AB or phi gamma CD system with the L matrix as the feedback. Now, where was the gamma minus LD term? Over here. Z equals gamma minus LD times U. So gamma minus LD coming in. See that? So it's again an equivalent block diagram. And that's the estimator. Now, when you construct and use estimators like this, you're looking for the state vector output. But because it's a difference equation, the state vector at time k plus 1 appears here, and the state vector itself appears here. What people do is use this one, right? Because it's in the most recent sample period. The most recent sample period. So that's the newest state vector, and that's the one that's always taken. Right? You can take the other one, but why wait? Get the most recent sample that you can. Now, there is similarity, you'll have noticed, between some of the equations for estimator design and for controller design. The eigenvalues of the estimator are at phi minus LC, and the eigenvalues of the feedback controller are at phi minus gamma times k. And I've explained previously the property of duality, which we can now exploit for estimated design, because the dual of the system phi gamma CD is phi transpose C transpose gamma transpose D transpose. And not only that, but the K and L matrices are related by a transpose as well. So estimator design is the dual of controller design, and we can use exactly the same techniques, because if you had phi minus gamma k to design your feedback gain matrix, replace phi by phi transpose, replace gamma by C transpose, replace K by L transpose, and just transpose the lot, and you've got exactly the same equations. So you can use the same techniques. Where are the estimated poles? Now, the job is very simple. Just like before when we used the manual process for pole placement for K, and we insisted that the matrices be in controllable canonical form, we ended up with a nice simple relationship between the coefficients of the actual eigenvalue and the desired eigenvalues. You can do the same thing for an estimator, but we really need the system matrices to be in observable canonical form. So remember, this is a CCF matrix transposed. So this is phi transposed. So all of the coefficients appear in the last column. This is effectively B transposed, and this would effectively think of it as K transposed. And so when we compute the closed loop eigenvalues for the estimator, phi minus, for lambda I minus phi plus LC means we're computing the determinant of this, and because we've got everything in the last column, it turns out that the estimator eigenvalues are the solutions, at least the single output case, to this polynomial down here. So you can use this in the same way as we did before. You select the eigenvalues you want, and you just match the coefficients across. So here are the estimator eigenvalues you've got, placed based on the elements of the L matrix. I guess I've animated this. Those are the estimator eigenvalues you've got. Then you choose the ones you want, and again you choose real or complex conjugate eigenvalues. That'll tell you what the factored form of this characteristic equation is, expanded out, and now it becomes a matter of matching coefficients. For example, C sub n minus 1 becomes L sub n plus A sub n minus 1. L is the quantity you want, so it's just a question of matching coefficients and calculating what L is. You can do it by hand. Just as we used Ackermann's formula for controller design, the feedback matrix, so we can apply it to the estimator to produce the elements of the L matrix in exactly the same way. So let me quickly show you that. And I'm going to show it in tutorial 8.1, which says for the double mass controller, design a digital estimator with eigenvalues faster than those specified for the closed loop system. And if you remember, we had eigenvalues 0.3, 0.4, 0.6, and 0.9. So we would want our eigenvalues to be significantly faster than that. So let's do this. We're on tutorial 8.1. Again, we're computing the exact same equations as we had before, and this time we're assuming that we're not using integral control here, we're just using the K and N matrices. So there's a reference input matrix here which removes the steady state error. And the first step, of course, is to check observability. So we check the dimension of this system, which is 4, build the observability matrix, and then check that it has rank 4, and indeed it does have rank 4, it's observable. And now what we'd have to do is to use Ackermann's formula using place, but we have to select the eigenvalues that we want the estimator to have, which will affect the speed of convergence of the estimator error. And so the smallest eigenvalue for the feedback controller was 0.3, so let's make them all smaller than that. They're all closer to the origin of the unit circle. We'll use 0.1, 0.15, 0.2, and 0.25. And now we will use the place script to use that to apply Ackermann's formula, but now we've got some transposes. It'll produce for us L transpose, which is the dual of K, and we have to give it C transpose, and then transpose the whole result, which is what's going on in that line. So this should give us the L matrix, which should be an n by 1 matrix. There it is, n by 1. And there are the numbers. We don't have to be so alarmed by big and small numbers now, because they're just numbers. The computer will handle it. Now let's verify that we have indeed got the eigenvalues where we want them to be. And we have, because I wrote the script, and I wouldn't be showing to you if we hadn't got that. And now what we'll do is open the Simulink model, because I'm going to simulate everything from now on. and show you what's involved here, I guess. Perhaps that. Okay. So here it is. I was wrong. We're using integral control. Yeah, I am sorry about that. I was completely wrong. We are using integral control, and I should have recognized it because the N matrix here was different. Remember before when we did the reference matrix, it was 11 point something, and we redesigned it. So it is actually and also these numbers are different. They're not the ones that we had before. We are using integral control now, from now on. I apologize for that. So here it is. It's the integrating controller, discrete time, and I'm collecting the real outputs and the real states into the workspace, and we're going to use those a little bit later. And down here, we're using the estimator algorithm, where I am bizarrely using the state from this point, not this point. But anyway, I've got a one sample delay going on that I hadn't realized until just now. But it produces the state vector for us through K, and then we're applying feedback control just as we did before. So let's produce that. There it goes. And then back into the workspace here. What we'll now do is some plotting. We'll plot the output of the real states. So the real states that I'm looking at here are the mass positions Y2 and Y1, right? And I'm comparing them in a different figure with the mass positions M2 and M1 again. So Y2 and Y1, Y2 and Y1, these are real and estimated positions. Let's see what they look like. Well, there are the estimated states, which are actually mass positions. And here are the real states, and they look, don't they, surprisingly similar. So what's happening in this case is that the input is a function that goes from 0 to something and then back again. What we're seeing is that we'd like the output, Y2, which is the position of the second mass, Y2, to do the same thing. And it does, but it's got the eigenvalues of the system to contend with. So it's got 4 real eigenvalues there, so it's a kind of exponential response. And this is effectively what mass M1 has to do to get it to do this. And they do approximately the same thing, don't they? I mean, they look estimated and real, they look pretty similar. So let's go ahead and extract a little bit more information and see if it's doing the right thing. We'll plot now the state error, which is the difference between the real and the estimated mass positions. Pretty small, right? So that's rather encouraging. Okay, so there's some initial state error. This might be initial condition error, or it's just the estimator settling down, but after that, the error is very small. It's not bad at all. Pretty impressive result, I think. And then finally, we'll plot the outputs on top of one another. So this is Y2. This is the mass M2 position, and you can see apart from a little bit of error at the beginning, we're pretty good because there's a blue and a green line, and they lie on top of one another. So this estimated design is doing exactly what we hoped it would, providing the whole state vector for use in that integrating feedback controller. So what you're proposing is to put an integrator where? So you're going to change this vector based on that. Is that what you mean? And what would that achieve? That's what we're doing here. That's the error between the actual output and the estimated output. And what you're proposing is to do another feedback loop from here. So that's X hat there. So take that where? Well, L, remember, fixes the eigenvalues here. So if you change L, your eigenvalues change. Yeah. I don't think that's going to work. Now, maybe there are other structures. Actually, there are many other structures of estimator. What I'm presenting here are linear state estimators. You can get a lot more inventive than this, but they tend to be non-linear and time varying and things like that. And I'm not going into that detail here. I'm just thinking. This one? Well, it's a discrete, it's just an algorithm. So, you're asking about the sensitivity of the entire estimator to the quantization error here. I have no idea. I mean, it will be sensitive, but in fact, it's the quantization here, I suspect, that will happen, because this is going to be part of the estimator algorithm, right? So you're producing an estimator there. You wouldn't, put a D to A converter in it, so you would just have that. That would be measured. It is going to contribute to the error, that's true, but you would need a more thorough numerical analysis to work out how sensitive it was. You'll get, so if I've taken the feedback from here instead of here, it will be a slight improvement in performance. It will be a slight improvement in performance, yeah. Just coming back to your question for a moment, of course, if you didn't have the estimator, if you were able to measure all of these states, you'd have exactly the same contribution, the same problem. You'd have quantization error no matter which signal you fed back. You've got to feed something back. Yeah. Okay. So let's move on now. That was called a prediction estimator. Oh, rats, we've got one more thing to do. I only told you about the single output case. And you're going to hate me for this, but there is also the case where you have multiple outputs, and in that case, guess what? We use eigenstructure assignment, which I'll do you the favor of not stepping you through in quite so much detail as we did before, but it's based on exactly the same set of rules. All you do is exploit the property of duality to apply it. So every time you saw K in the previous slide, you replace it with L transpose, and every time you saw gamma, you replace it with C transpose, and every time you saw phi, you replace it with phi transpose, and nothing else is different. It's all exactly the same, except now you've got L transpose here, so you're going to have to transpose the result once you find Fg to the -1. I'll quickly do it because I don't want you to think that I'm sidestepping this issue. Oh, come on. Right. So the tutorial now, I'm not going to use the flight control example because nobody in the right mind is going to use an estimator for things like this in a flight controller. But this is a third-order system with 2 inputs and 2 outputs, and therefore the fact that there are 2 outputs means that we need to use the eigenstructure assignment method, and we want to ensure that the estimated state converges on the actual state within 1 second of this. And so I'm going to quickly do this as a tutorial. Again, we'll construct the system matrices in MATLAB and check observability, and you won't be surprised to find that we have observability, otherwise I wouldn't have written it. And now we're going to choose the eigenvalues. Now, just to make things difficult, I've chosen a pair of repeated eigenvalues. I want -8, -8, and -10. And you can do that, but you're slightly less flexible in your selection of the eigenstructures because you've got 2 of these eigenvalues rather than 3, and so you're going to end up with 4 columns rather than 6, because you're going to have each eigenstructure has got 2 columns because it's a 2-output system, but you've only got 2 eigenvalues instead of 3. So what you've got to do is select both columns from one of the eigenstructures and only one from the second eigenstructure. So you've only got 4 columns to play with. So when I build this, it's a 4-column matrix that we've got to play with. And we will choose columns, let's separate it out first and then calculate the least cost way through. And I'm going to select columns 1, 2, and 4 because 1 and 2 both come from the eigenvalue -8 and 4 from -10. And so we'll do that. And then we'll invert it to find the L matrix. So it's a 2-output system, so we've got 2 columns, and it's third order, so we've got 3 rows. And we'll verify that the eigenvalues are indeed where we want them. They are -10 and 2 and -8. And now what I'm going to do is I'm going to deliberately force an initial estimation error by making the initial conditions of the estimated state vector different from those of the plant. I could have done it the other way around, which is probably what you would have seen, but in reality, but there's a difference, and that's the important thing. And so now what we're going to do is to simulate this and check that it's right. Okay, so nothing very different here, except that we are not using integral control in this example. All I'm doing is I'm applying fixed values to the two inputs to this system. There's no kind of dynamics going on. All I'm looking for is convergence of the states. So we'll do that and then plot the results. And here we have, because we've selected these eigenvalues relatively far to the left, three states which for some initial condition error will converge on zero error after 1 second, which is what we're looking for. And the fact that the 1 second rule has been respected is because these eigenvalues are relatively far to the left, and I calculated what each of them will produce based on a first order approximation, because you know what the settling time is. It's four time constant. So within 2%, and that's what it gives me. Now, I'm going to repeat this, but I'm going to do it for some error in the plant model. So let me show you what happens when we've got errors in our plant matrix. So what I've done here is, first of all, I've created the original thing with the same gain matrix that I've got and the same initial conditions, and then I am simulating and plotting the results. Let me go through this again. So there we are, we're no further forward yet. Now what I've done is deliberately introduced some error into the system matrices and the state matrix and the input matrix, and created a system with some error in it. Okay, so I've been very Machiavellian and put some error in there. And now what we'll do is resimulate this, because now what we've got is a situation where the estimate has been designed using different matrices than the system actually has. And when we plot the results, we'll find that the convergence is the same as before because the eigenvalues are where they need to be, but there is a steady state error, and that error is because we've got imperfect knowledge in the system matrix, knowledge of the system matrices. So this feedback thing gets rid of initial condition error, but it doesn't compensate for errors in the system matrix, our knowledge of the system matrices. Okay? Be anything like that. Yeah, it could be anything like that. Temperature, time dependence, wear, there may be aging effects, anything like that. Or, just as likely, you don't have perfect knowledge of the system. You know, you've got nominal values to work with, but maybe there are component values that are not, exact. So maybe something like that. But every system's like that. Every control system's like that. I don't know how you would apply an integrator to an estimator to get rid of them. How do you know what the right values actually are? There's nothing that you can input and output of what? I mean, we don't know that we have this error. We only estimate this error based on what we think the plant states are, because I'm in a very happy situation here of having a model, right? And this model produces for me the real states. I don't know what these are in the real situation. They're internal to the system description. I can only present it on the slide, on the MATLAB diagram, because I know that. So in a physical system, what have you got to integrate? I don't think you've got anything. That's what you're doing. That's what you're doing. So you take the output here and subtract it from what? Input this. So that minus that. Well, that was integral control, wasn't it? Yeah. That was integral control, but it's not going to guarantee that the estimator produces the right value. Yeah, anyway, I don't think that works. Okay, so far we've been producing estimators called current estimators because we've been using y of k in the computation and producing x hat in the k plus 1 sample interval. So if you like, we've been predicting x hat of k was based on y of k minus 1, x hat of k plus 1 was based on y of k. So there is a one sample delay between the output being measured and it being used in the computation of the estimated state. What we'd like is to be able to use the existing, the y of k in the existing sample interval to estimate the state in the same sample interval, and that would be called a current estimator. Now, when we do this, what's different is that instead of y of k up here, we've got y of k plus 1. And it's not difficult to see what's going to happen next, because y of k plus 1 equals c times x of k plus 1 plus d times u of k plus 1, right? Well, you know what x of k plus 1 is. It's phi times x of k plus gamma times u of k. So I don't think I need to write this out, do I? L times y of k plus 1 is L times c times x of k plus 1. Well, that's x of k plus 1. Phi times x of k plus gamma times u of k, plus L times d in the k, d times u of k plus 1, plus c of k. Okay? Now, we can collect some terms together here because we've got, actually, no, we can't. We can't yet. What I'm going to do is to do the same as before by looking at the estimator error. So x of k plus 1 minus x hat of k plus 1 equals, well, x of k plus 1 is phi x of k minus gamma u of k minus all this other stuff that was up here in this equation. And now we can do some collecting together. We can say phi minus LC phi, and already we can see what the principal difference is with the current estimator. The eigenvalues are going to depend on another power of phi in this, inside this matrix. That we're going to choose to be the same as phi minus LC phi in just a moment. And then there are terms over on the right here that have been collected together. And these are inconvenient, so we're going to choose z of k slightly differently. We're going to choose z of k to be equal to all the stuff we don't want. There's u of k principally, but there's now two different sample intervals involved over here. That's okay, we'll get rid of that in a second. And we choose phi e to be phi minus LC phi, so we've got back to the first order difference equation in which the feedback matrix L determines where the eigenvalues live. Okay? So this is what it looks like in a block diagram form with these definitions. Yeah, there's nothing to say. The principal thing here is that well, the D matrix doesn't appear around here anymore because it's wrapped up in Z of k. And this is an unavoidable thing, unfortunately. There are addition, because the U matrices are by 1, there are additional delay elements present whenever you get a non-zero D matrix. So there you go. That's the current estimator. And so the design of that doesn't look too different from before. It's just that the system matrix is a little bit different and the structure of it's different inside as well. Now, unfortunately, there is a problem with this because if you think about it, everything now is in the same sample interval. I've got the estimate of the state in the k plus 1th interval. I've got the measurement of the output in the k plus 1th interval. And I've got the input in the k plus 1th interval over here. So can you see what's going to happen? Right? I estimate the state, which is needed to produce the input u, and the input u defines what y is, and I needed y in order to produce the state estimate. I'm in this endless loop here, because everything's happening at the same time, and I don't know what to do first. It's called an algebraic loop. And the way you get around it is to insert a delay. You have to put a delay somewhere. Now, you can experiment with this if you want, try it in various places, but the place you have to put it is in here, so that u of k becomes u of k minus 1. And if you do that, the equations change slightly, but you still take advantage of the most recent sample, output sample, in your computation of the state vector, and that's how you do it. So let's quickly do a tutorial on this, and I think the tutorial is based again on the double mass damper. We're just going to convert the estimator to make use of the most recent output sample. There's nothing very surprising. It's still the same integrating controller with the same matrices. we're still going to use the same choice of eigenvalues, except that now we're going to check them against phi minus LC times phi. That's the system matrix now, not phi minus LC. And when we check them, we should find that hopefully they're in the right place, 0.1, 0.15, 0.2, 0.25, and so on. So let's simulate this, and the structure of the estimator is going to be different now because it is using this. So here you've got the additional delay that comes in and the additional delay that needs to be present in V of k. So that part of it is a little bit different, and the rest of it you've seen before. So when I simulate this using the matrices that we've just defined, there we go. Let's hop back into MATLAB and plot the results. The estimated and the real states are still similar. There's no apparent difference from what we had before. And if I plot the error, the only difference between this and what you had before is actually this error is smaller than it was before. It's hard to see here, but I think I can show you it if I look at the outputs, because you may have noticed before that there was some visible difference between the green and the blue, and it's a lot smaller now. And that's really where you win with the current estimator. It gets rid of the initial estimate error much faster. That's the principal advantage of using the current estimator. Okay. Unless you're using a sample rate which is comparatively slow compared with the dynamics of the system, you're not likely to notice a big difference between the current and the prediction estimator performance, except in the initial condition convergence. But if you are, you will notice big differences. But here you can see the dynamics of the system are much slower than the sample rate we're using. So we're not seeing any difference really here. Okay, the next way that we're going to look at improving estimator performance is not through performance so much as efficiency, code efficiency. And this is useful in cases where some of the internal states appear at the outputs, and we then can redesign the estimator if we want to make use of some computational savings by only estimating the states that we can't measure. And so if we've got some of the states appearing in the output vector, it makes sense to use those directly and then simplify the estimator so that, well, we still make use of the output and the estimator is still in a feedback loop as it was before, but it's computing a smaller state vector than was previously the case, and so the estimator equations are fewer in number and hopefully smaller as well. So it's a computational saving that you get back from this. It's called a reduced order estimator. And once again, I mentioned the fact that you may not always want to do this even when you can, because the benefits of computed states are that it's not subject to electrical noise or that type of thing, or disturbance, in the same way as measured values are. Now, it's quite complicated to design this. You have to get your head around some weird concepts, but let me explain how you do it. The first thing that you need to do is to reorder the state vector so that the measured states appear in the first elements of X. So X1 is a partition of the state vector which is measured, and X2 is an unknown partition which we have to estimate. Now, you need to reorder the states to do that, usually, and that reordering can be performed by a matrix called a permutation matrix. All it's doing is reordering the states, and a permutation matrix has the properties of having, it's a square matrix because it's going to change an n by one vector into another n by one vector, but you can recognize them because a permutation matrix has, each column has all zeros except one number, which is a 1, and every row has every zero except one number, which is a 1. That's a permutation matrix, and so you position the zeros and ones in nice places that give you the reordering that you want. But you can always do this. You can always find a permutation matrix which reorders the states. And therefore, the partition state matrix looks like this: phi11, phi12. So it's partitioned according to the selection, the measured and unmeasured states: phi22, phi21, phi22. Same with gamma, and the same with C. C now, I and 0. I means that we've got direct coupling between the input and the output, between the state and the output. so the states are being measured. And this, I'm assuming, is 0 for now. It doesn't have to be 0. It doesn't really matter. It doesn't affect anything that's coming. It might not be, but this has to be the identity matrix because we've got to be measuring those states. Okay? The transformation which reorders it is called a permutation matrix, and it's used in the similarity transformation down here. Okay, so you do this. And what you've also got to remember is that the feedback gain matrix you've designed without reordering the states. Right? So once you've estimated what the state vector is, you've got to use this. Either you've got to use this permutation matrix again to put the states back in the original order, or you've got to reorder the K matrix using the permutation matrix so its elements are in the right order. And usually do the second one because you only have to do that once. So here is the full system equation pair written out in matrix form, in partition matrix form. And so what we'll do is we'll begin by expanding these matrices out. So here are the two state equations. X of k plus 1, remember, is measured. So, and x 2k plus 1 is not measured. But just concentrate on the system equations for now, because I'm going to tweak these quite a lot. Now, what we want is a form of matrix of equations which recognize that x1 is known and x2 is unknown. Okay? And I'm going to separate out the known and unknown parts and make them look like a different set of system equations. And here's how you do it. First of all, the second of those two equations, that's unknown, this is known, that's unknown, and that's known. Right? So what I'm going to do is bring, in the second of these equations, this term to the front. So I've got x2 of k plus 1 equals c22 times x of 2. So it looks like a difference equation, right? Just involving x2, the unknown bit. And then the bits over on the right are known. And then that's what the first equation is going to look like. And then the second equation, the only thing that's unknown in the second equation is x2 of k. In the first equation is x2 of k. So that's going over on the right. I'm going to treat this as the new output. See, you've got to get your heads around this. It's not that difficult once you think about it. What you've done is made the second equation look like a state equation, and the first equation look like an output equation. So now you can define a sort of new system matrix, which is phi22, and a new sort of input matrix. Well, it contains x and u. Don't worry about that yet. That's called gamma sub r, that matrix there, times u of k. And then that's the output, and that is the new output matrix. Phi12 plays the role of the C matrix, so it's the reduced order estimated C matrix. So you could now... in the first equation, yes, exactly what I'm doing. Yeah. And in the second equation, well, this x2 is unknown, so yes. But this is the new output. I'm just treating that as the output for now. Right? And I'm going to use these new matrices in just the same way as we did before to find what the matrices should be. Right, here we go. The same prediction estimator that we had before. And what I'm going to do now is use y sub r and phi sub re. Use those definitions that I've just had in the previous slide. So x2 hat of k plus 1. Right, that's the, this is the estimator equation now, because we're just going to produce x2 from this, is phi minus LC, so phi22, because it's phi r. Right, phi r is phi22, minus LC, and C is phi12. So when I look at phi minus LC, it's going to be phi22 minus LC, LC12, times x2 of k, so that's that part, plus L times y sub r of k. Well, the previous slide I showed you what y sub r of k was. It's all that. So L times all that, plus z of k. Well, that's gamma times u of k, remember, in the prediction estimated case. So it's this term here. Weird, isn't it? But it actually works very nicely. This is z of k, and it's gamma times u of k in the prediction estimated case. So this is what we've got to work with now. Now, funnily enough, it's not quite the end. We have to form the estimated dynamics, which is now phi22 minus L phi12. So now you know those partitions because they're from the system matrix. You can design L to give you the estimator eigenvalues that you want. You specify them freely. and they'll be the same providing that your original system was observable. You've actually got fewer eigenvalues to find because you're only producing the X2 partition, which is n minus however many states you're measuring. Now, funnily enough, most books leave the equations in this form, and it's kind of a long, unwieldy form to get to, but you can simplify this quite a lot because you've got several terms involving x1 and several terms involving u, and if you simplify this, I haven't seen this done anywhere else, but if you do simplify it, you can write it in this form here by making some, collecting some formulae together. So phi to 2 minus L phi 1 2, call that phi RE. Let's call this term LRE, no reason, and this term gamma RE. And now you've got these three matrices instead of about 10 that we had before, and you've just made a few definitions. Because it's a linear time invariant system, these are computations you just carry out once. And now these three matrices are fixed. They're unchanging. And this is what the structure of it looks like. So you've got this. See, one other thing I forgot to tell you is that this term here appears in the k plus 1 interval just like that does. So I've taken it over onto the left and said x2 had a k plus 1 minus Lx1 of k plus 1. Remember, x1 is measured. So this kind of looks a little bit strange at the moment because you've got two terms on the left, and until now we've been dealing with a difference equation with only one. But because you know that, you can calculate what this term is and then add that in later, which is what's going on here. So we're going to calculate this, and then once we've calculated it in the kth interval, I'm just going to add in L times y of k, and that term disappears, and I'm left with x2, which is going to be the output. So you see? And then these other three matrices, they just sum together. U of k comes in through gamma RE, and then you've got LRE and phi RE like that. And I think you'll agree that the actual structure, because you've only got three matrices now, is a lot simpler than if we'd done all that with all those other matrices in it, which is how you normally see it in books. Just a lot simpler that way. Let's see how it performs in an actual situation. And this is the very last tutorial of today, so I hope you enjoy this one. So once again, nothing surprising, we're creating the model of the system. We'll do that. And now we've got the permutation matrix necessary because we want to reorder the states. I want to put the measured output as the first state. And in this case, I'm looking for mass 2 position to be the first state. So I've got 0, 0, 1, 0, 0, 0, 1. So what I'm making is x1 in the new state vector becomes x3 from the old state vector. Are you with me? So now mass 2 position is the measured output, and I don't need to estimate that anymore, but the other three states I do need to estimate. So I'm just swapping those pairs around, and that's what that permutation matrix M is doing. And then down here I'm forming these matrices that I need for the system. Okay, so there you go. There's a new matrix, reordered matrices. And now we've got to create the partition matrices. So there's the phi matrix and the gamma matrix. And what we'll do first is check the observability of the system, which we know is going to be observable because I told you that the full system was observable, and if that's the case, then the reduced order system is automatically observable. And now we only need to select three eigenvalues because we've only got a third order estimator now, so we'll choose the three fastest ones, 0.1, 0.15, and 0.2, and use Ackermann's formula to place them and check that we've put them in the right place. And how happily we do have the eigenvalues that we want. And now all we need to do is to remember that we've got to have a new order of states in the feedback gain matrix. We've got to adjust the states there to take account of the fact that you've reordered the states. There you go. And what we'll do now is simulate this and see if it works. All right. Now, it actually does work, but let me just look at it a little bit. Okay, here's the estimator part of it. It's the part we've designed. And you can see that the output of this is a scalar quantity, so that's going to stay as a thin line. And when we take the estimated states back into the workspace, That'll be the first element in the state vector, and the other three elements will come from the estimator. And so this, what's coming back through this feedback gain matrix is the entire state vector down here. And I haven't actually bothered to simplify this, but if you can simplify it and get it to look a lot simpler than that. But this here is the x2 hat k minus 1 minus L times x1 of k plus 1. So we're adding in L times y of k plus 1 here to get the actual state vector that we need. So let's run it and check that the thin lines turn thick where they're supposed to. All looks good. And now let's plot the real and the estimated states. Okay, they're the estimated states. They're the real states. There's nothing terribly exciting so far. They're the complete states. Now we'll plot the state error. Okay, state error is small, right? 1 times 10 to minus 14. I don't know why it's bigger up here, but the masses are moving in this area. So I think this is just perhaps within the computational limits of the tool, but these errors are very, very small indeed. So the estimator seems to be doing its job. And finally, we look at the control effort, which is there. You know, it's what you want. You're trying to position it so that it follows that step, which returns again. So initially, you've got a little nudge in one direction, and then it corrects itself, and then it does the opposite when it comes back. So that's the thing. And that's how you do it. I mean, there's not much to all of this. It's just a question of following a procedure to arrive at the right matrix values. So the reduced order estimator, once you calculate the equations, will have fewer equations in it. Yeah, it's faster, less computational load. The minimum saving you get is 5 partial products. I've worked it out. But the maximum saving can be large if the order of the system is large and you're measuring a lot of states. It's usually worth doing, even if it's only for 5 partial products. So to conclude, I'm just going to summarize what we've done over the last couple of days, today anyway, in terms of control system design. We typically proceed in 3 steps. The first one is the design of a feedback gain matrix to achieve satisfactory transient performance by selecting the gain elements to give us the eigenvalues that we want, assuming that the state vector is available. The second stage was to design an input matrix which took account of the steady state error, and also at the same time allowed us to adjust the steady state. And we saw that with dead reckoning, assuming we knew exactly what the elements, the matrices of the plant was, we could do this, but it was not all that simple if we didn't know it. So we could, in some cases, use integral control, assuming that we had correlation between V and Y. That may or may not be possible. And then the third step involved estimating the state vector because we didn't have it available, so we used the output in a negative feedback loop around the estimator to produce the state. So we have now 3 separate steps in the design process. Now, recall that K fixed the controller eigenvalues, the closed-loop control eigenvalues, and that the estimator had its own set of eigenvalues, which is bound to influence the closed loop. So you choose the estimator eigenvalues to be faster than those you designed when you designed K. Well, who's to say that inputting an estimator in the loop that you haven't changed the closed loop eigenvalues? Who's to say that? All I've shown you is how you design the closed loop knowing that what the state vector is, and how you've designed the state estimator to have its own eigenvalues. Who's to say that putting these in didn't influence the ones you chose from K? And in fact, they don't, and the justification for it is contained in something called the separation principle, which is not derived, but at least stepped through in the book in a little bit more detail. And what it says is that the eigenvalues of the overall thing, including the estimator, are in fact the product of the closed-loop estimator, closed-loop eigenvalues, the controller eigenvalues, times the estimator eigenvalues. So you can separate them out. In fact, the separation principle is the justification for proceeding in 2 different steps, controller first, estimator second, because they don't influence one another. And that's why you can select them independently. It's called the separation principle. There are the controller equations. I think this is perhaps for reference only. And I've given you an example of how they might be constructed. I just want to point out to you I've made a mistake in the structure of this. If you transpose this, see the gamma matrix has to be gamma 1, 1, gamma 1, 2. So it's a 2 by 1 matrix, and then these equations work out. But otherwise, it's correct. Or for reference anything. And let's complete this section with a quiz. Which property ensures that the states can be reconstructed from measurements of the output? Observability, that's right. If the system is observable, you can build an estimator and estimate the states. What matrix defines the dynamics of the linear full-state estimator? Let's assume that it's the prediction estimator for now. And we're selecting the eigenvalues of the linear prediction estimator. I think it says prediction, but you can give me the current as well if you want. It's phi minus LC in the prediction case, and if it's the current estimator, it's phi minus LC times phi. It's just a memory test, but you would get to know that after a while. Which principle allows us to use feedback control equations for estimator design? We used Ackermann's formula, didn't we, when we designed the feedback controller in the single input case, and we used it again when we designed the estimator for the single output case. Why? What property allowed us to do that? Looking for a single word. Duality. Spot on, you got it. You knew all the time, didn't you? It was duality. The estimator design equations are the dual of the controller design equations, and duality allows us to use the same principle, the same methods to design estimators as we've used for feedback controllers. When can you use Ackermann's formula for estimator design? What must the system be in order to use it? Sorry? The single output, actually. Single output. The inputs don't come into it. It's the output that's necessary. Single output, that's right. When might it be preferable to estimate states even when you can measure them? Yeah, that's right. It's because the measured states are susceptible to noise and disturbance in that the estimated states are not. So there are times, I mean, it's not always the case, but there are times when it's preferable to have a full state estimator, even when some states are measured. And what's meant by a prediction estimator? Remember the linear state estimator equation? We had x hat of k plus 1 on the left equals phi e times x hat of k on the right plus L times y of k. The point is that you're not using the most recent output measurement when you predict x hat of k plus 1. So we replaced y of k with y of k plus 1. So rather than predicting what the state was one sample period in the future, we're using the current measurement in the same sample interval as we estimate the states. So a prediction estimator has got this one sample delay associated with it. In the context of control loop design, what is meant by the separation principle? What does it tell us? Yeah, that's right. So you can design the eigenvalues of the controller independently from those of the estimator, and neither interferes with the other. Of course, both contribute to the eigenvalues of the overall system, but you don't change one set of eigenvalues by designing the other. And the two principal control objectives, who remembers this from day one, slide 1? You're getting there, it's almost right. Reference tracking was 1. Don't you give me the second one. Reference tracking was 1. What was the other one? Oh, almost. Disturbance rejection. You want perfect reference tracking in the face of disturbances, be they noise, changes in load, parameter variation, whatever they are. Those are the two principal control objectives. Before I let you go, I just want to conclude with a couple of points in general about this seminar. First of all, a congratulations to all of you for the amount of stamina that you've shown in the last 2 days. I know how difficult it is to have this amount of information coming at you all at once, but I hope that the books that you've got will be useful to you afterwards to go away and look through them. And by all means, please email me if there's any questions. Get in touch. Don't hesitate. I'd be delighted to help. So 2 days of hard work. These are the books that I recommended for yesterday's seminar. I'll take you briefly through 3 books that I think might be helpful for state-space control. The first one, and I think the best book that's been written so far on state-space control, is called Modern Control Theory. It was written in 1991 by William Brogan. And it contains, I think it's a compendium of everything that you will ever need to know about state-space control in the world. It's the single best book that there is. There is a book that's been around for slightly longer by Franklin Powell and Workman, which concentrates on digital systems, and it includes not only state-space, but a lot of the digital techniques I talked about yesterday. I think it's out of print at the moment, but you can pick up a very good copy secondhand, really cheap, and if it's out of print, they'll probably put it in print again at some point. It's really, really good. But most of that content is state-space, and it deals with estimation and also optimal control and some other topics in control as well. It's a very, very good book. And the third book here is one by Astrom and Murray called Feedback Systems, and it's a much more recent publication, which, and I don't know why, but you seem to be able to download the PDF online completely legally. So take a look and download it if it is free. I think you can. The reason that I recommend this one is that it does a much better job than I've done of connecting the state-space concept to physical examples. And he picks a very diverse range of physical systems to work with. He's got animal population growth models, he's got medical systems, he's got all sorts of things in there. And he does it in a very, I'm envious, a very engaging kind of a way. Doesn't deal with transfer functions at all. It's based entirely around the state-space approach, and it's actually a very good read. So that's called Feedback Systems. There are a couple of other seminars which you might see around at some point or another, but keep an eye on the website, controltheoryseminars.com, because I always list the upcoming events in there, and if there are new publications or stuff that I've added to the seminar, I'll put them up there, and where I can, I'll make them downloadable. Please get in touch if you've got any questions. That's my email address, polyshark@gmail.com. Long story, but that's the email address. And with that, I wish you the very best of luck. Thank you very much for your attention in the last 2 days. Please stay in touch, and I'll be emailing all of you once the recordings are available on the web, and I'll be glad to get in touch with you. Yeah. Yes. Right, so for stability, you're looking for poles in the stable region. For robustness, it is not simple. It really is not. The techniques get much more complicated when the systems are multivariable, and they're well outside the scope of what I can do with here, I'm afraid. For single input, single output systems, as well, for single input, single output systems, there are some nice graphical techniques in the second book that are recommended from the first day, in the Doyle, Francis, and Tannenbaum book. There are equivalent techniques for multivariable systems. I can point you towards a book by Skogestad and Postlethwaite called Multivariable Feedback Design, but you won't get very far into that book before you realize it's a much more complicated undertaking. So I can't give you a clean answer to that except pointing in the direction of some books. Sorry about that. Okay. Anything else? Yes. Yeah. If it's not exact, well then, the estimate of the state will be incorrect, and there will be errors in the control loop, which will mean you'll have imperfect control. Now, those errors are steady-state errors, principally, and so if you're employing integral control, if you're lucky enough to be able to do that, because you've got the right geometry between the correlation between the inputs and the outputs, you can take account of that, but your control will be compromised somewhat. There's no doubt about that. Yeah. Well, there are all sorts of advanced techniques that I haven't gone through here, and I'm afraid I'm not able to comment on the improvements that you might see by using some of them. But for sure, if you have You are going to have imperfect knowledge of the plant matrices, and there is going to be some error. Hopefully that error is small enough that it won't significantly impact on your control, but there will be some impact. There's no question about that.
Well, that would be like AR and ARMA.
They are used quite a lot. Yeah, ARMA is not an adaptive technique. That's the structure of the controller. But you they are used. Yes, very definitely. That's outside what I've been able to talk about. Oh no, I don't. Unfortunately, I don't have specific examples like that. Sorry. Okay. Anything else? All good. All right. Thanks once again. Then we'll wrap it up here. Have a safe journey home, and please do stay